Thank you. Thanks for coming. I leave on Wednesday, so I swear this is the last time you have to. When I started this, when I gave my first talk 2 weeks ago, I explained that this project on analytic wismatization had two main motivations. One is a p-adic Hodge theory of rigid analytic varieties and trying to mimic what Bart Scholze, Bart Lurie, and Greenfeld did in this in the context of p-adic formal schemes, but in the world of rigid geometry. And that was like the main focus of our lectures with Maximilian. But I also said that another motivation for us was understanding the geometric aspects of the p-adic Langlands program. And for this, the work of Lue Pan was a big source of inspiration. And so some of the goal of today's talk is to maybe explain the relation, part of the relation between what Maximilian and I discussed over the last 2 weeks and what Lue has explained to us in this seminar in the last 2 weeks as well. Okay, so the work of Lue is about completed cohomology of modular curves. And we know in this particular situation by the work of Matt Emerton that in the completed cohomology of modular curves we see the p-adic local Langlands correspondence for GL2QP as has been constructed by several people, maybe most notably Breuil and Kolmez. And at places away from P we also see the smooth local Langlands correspondence. And this is a statement which is expected to generalize, but is also inspired by, of course, by no classical but still very deep results of Eichler, Shimura, Deligne, which describes the cohomology, let's say, with p-adic coefficients, the cohomology of modular curves, but at finite level in terms of the Langlands correspondence for modular forms. And although this is not rather standard, it's still the first time you see it, it's kind of surprising. Why would you expect the cohomology of these spaces to realize the Langlands correspondence, right? And I don't think this is a hard question. I don't think there is a simple conceptual answer to this. But I want to start by maybe explaining at least a different perspective, different point of view on this question, which is coming from the recent work of Hauck and Scholze. So that will be my starting point. And so to do this, we will replace modular curves, or more generally global Shimura varieties, by their local analogs, which are called Rappaport spaces, or more generally local Shimura varieties. And these kind of geometric objects have been defined much later than modular curves or Shimura varieties, but nevertheless it's easier to address the kind of questions I care about today in this context, just because in number theory local questions are always easier than global ones. So I won't be telling you much really about modular curves themselves, but really mostly about their local analog. And so the simplest and oldest example of local Shimura variety or Rappaport zinc space is Lubin-Tate space. So to fix some notation, let me denote by G the group GLN for some n bigger or equal to 1. I will also denote by mu the co-character, dominant co-character 1, 0, 0, 0 of G, and B will be the isocrystal over Fp bar. Over Fp bar, we'll just denote by small k, which is simple of slope -1. And so the definition of the corresponding Rappaport zinc space, which is in this case just Lubin-Tate space, is we look at something I would denote mg by mu. So it's a rigid generic fiber of a formal scheme so it's a rigid generic fiber of a formal scheme over ZP breve, the ring of integers in the completed maximal and ramified extension of QP, which I will denote QP breve. And this formal scheme is representing a certain moduli problem. So it classifies deformations by the isogenies of H, which is the unique up to isomorphism one-dimensional connected p-divisible group. Sorry, that's getting a bit small. Over K of height N. I will try. Yeah, so the justification for my notation is, of course, that B is the isocrystal which corresponds by Dieudonné-Manning theory to my P divisible group H over K. And mu, okay, like at least this one that appears just one time is related to the fact that I'm looking at one-dimensional formal group. And so, well, okay, this is represented by a certain explicit formal scheme. And you can also add level structures to this moduli problem by on the generic fiber by looking at trivializations of the Tate module. So by trivializing the Tate module of such a deformation, maybe the rational Tate module, one gets well, a certain adic space, which is not quite, it's not a rigid space anymore, it's not quite perfectoid, it's what is called pre-perfectoid. So it lives over QP breve. After you base change to any perfectoid extension, it becomes perfectoid. And this I will denote by MGB mu infinity, which is a Pro-étal GQP torsor. So G is just GLN, I recall, over MGP. Okay, so that's my local analog of a Shimoda variety. So a certain space of deformation of P divisible groups. And so, in the same way as we know or expect p-adic cohomology of Shimoda varieties to realize a global Langlands correspondence, there are similar theorems or expectations about the cohomology of such spaces, but involving the local Langlands correspondence instead of the global one. So that's the kind of statement I want to provide some kind of conceptual explanation for. And for that, I will state first a result that is due to Scholze and Weinstein. So for this, which gives an alternative description of this infinite level appropriating space, or Lubin Tate space. So for that, I have to maybe just first recall that by work of Farg and Fontaine, if S is a perfectoid space, perf is my notation for the category of perfectoid spaces in characteristic P, and let's say given living over Fp bar. Then there is a functor from rank n isocrystals to, so over K, to rank n vector bundles on the relative Farg-Fontaine curve over S. And if S is a geometric point, this functor is even essentially surjective. That's a classification theorem for vector bundles on the curve. And this I will denote by an isocrystal, let me call it B prime, because I already fixed B to be this specific isocrystal. So B prime goes to E of D. So for example, if you take B to be the trivial isocrystal, then EB is of course the trivial vector bundle, so sorry, B prime. EB prime is just is a trivial vector bundle of rank n on the Fark-Fontaine curve. And if B prime is B as above, then E of B prime is a semi-stable vector bundle of slope 1 over n on the Fark-Fontaine curve. I want this one to have slope 1 over n. This is why there's kind of change of sign when you pass from isocrystals to vector bundles.
Sorry, what is the superscript above the O for the isocrystal equals 1 case?
This one?
Yeah.
It's n, so just n copies of the.
Oh, I see.
Right, and so Schoenster-Weinstein, already more than 10 years ago, proved the following nice theorem, building on earlier work of Fark. So it gives a description, maybe not quite of this infinite level Rappaport-Zinc space, but at least of the associated diamond. Claim is that this identifies with a functor on perf K, sending S to, well, you look at all possible so extensions. Like modifications of the trivial rank n vector bundle by this semi-stable rank n vector bundle, such as the co-kernel is. Oh, sorry. Maybe I wanted to say. So this is naturally leaving our QP breve. So the diamond of NGB mu infinity is naturally leaving over the diamond of QP breve, and this means that I can see it as a functor on perfectoid spaces over QP breve. And if I have something perfectoid space which lives in characteristic 0, and let me denote by S the characteristic P perfectoid space obtained by tilting, and now I look at all possible extensions. Such that the co-kernel will be supported, so it will be an extension on the Fark-Fontaine curve of S, and recall that by this theory of Fark-Fontaine curves that this untilt gives rise to a degree 1 Carty divisor on this curve, simply because by definition S sharp is an untilt of S, and so I want this co-kernel to be supported at this point and to be of length 1. So W is rank 1. It's just a line bundle. So really the only thing that is moving here is just U. I just want to give myself a morphism between these vector bundles whose co-kernel is degree 1 supported at this point.
And just to clarify, is a degree 1, does that correspond to the one-dimensional?
Yeah, that's correct. Yeah, this corresponds to my choice of mu. Yeah. Okay, so that's a result that they prove. And it maybe looks, if you never saw that before, it may look very mysterious, but at least going in one direction is not that difficult. So if you have a R which is perfectuate ring, say, then basically the idea is if you have G, a p-visible group over, so if you have an R point of your MGB mu infinity, so it will be a certain p-visible group, so for the power bounded element, such that the mod P reduction comes with a quasi-isogeny to the base change of H and something, so right, you have a P quasi-isogeny. P, and you also give yourself a trivialization of the Tate module. Well, basically the idea is that the Tate module gives rise to a vector bundle, on the, so it's a QP module, so by base change the Fark-Fontaine curve live over QP. By base change you get a vector bundle, but beta gives you a trivialization of it, so that's just isomorphic to E1 beta. And on the other hand, you can also look at Dieudonné theory. This base change to R naught mod P of G corresponds to a certain phi module over the Fontaine's ring B plus Chris, which you can see as, more or less by definition of the Fark-Fontaine curve, you can see as a vector bundle on the curve. But the datum of alpha also gives you a rigidification of this. So maybe I just write like this, a bit imprecisely. So this is meant to be the Dieudonné crystal of G mod P. This is via alpha identified with what I denoted EV. And then what this modification is encoding is basically just this étal comparison, crystalline étal comparison for p-divisible groups, which relates the Tate module to the Dieudonné crystal and tell you that they are not isomorphic after base change to P plus quiz, but you need to invert T, which is related to the fact that this U is only a generic isomorphism and the co-kernel is supported on the vanishing locus of T. So that's roughly the idea, at least to go in one direction. All right. So for now, okay, just tell you another description of this infinite level Lue Pan Tate space. That does not seem too helpful yet, but so to give it a meaning, I have to explain, like to put it in perspective and to explain a little bit about Fark-Schulze. So Fark-Schulze defined maybe two main geometric objects. So Fark-Schulze defined two. I would say, they work with V stacks, but you can do everything in the context of arc stacks, which was the framework we've been using in the last 2 weeks. So I maybe want to stick to this. So stacks on the category of characteristic P perfectoid spaces for the arc topology. So one of them is Bun-G, which I will denote Bun-G Fark-Schulze because another Bun-G will appear later. And so this is just a functor sending S perfectoid to the anima of the groupoid of G bounded on the Fark-Fontaine curve of S. So this is indeed an arc stack by results of decent results of Kedlaya and Liu for vector bundles on these relative curves. And the other one is something I will denote by div1 Fark-Schulze. So it sends S to the. So this one is actually a shift to degree 1 Cartier divisors on Fark-Fontaine where by definition a degree 1 Cartier divisor is a Cartier divisor on Fark Fontaine S, which is coming from an untilt of S. So it's just a moduli of untilt of S up to Frobenius. And the two maybe main features of this definition. So, by the way, here you can just take G to be GLN. This was my choice, but of course, most of what I'm going to say works as well for any reductive group. I try to use notation which somehow still have a meaning and are the usual notations for generality. So maybe the two main features I want to briefly recall are the first one is that so inside Bun-G, so you have a stratification. So Bun-G has a so-called Hardon-Narasimhan stratification. And okay, which I won't really sorry, Bun-G Fark also, but maybe most importantly for today, inside Bun-G you can look at the semi-stable locus. So this is actually an open substack, and it's really explicit. It's just a bunch of classifying stack. So this is parameterized by the basic elements in Kottwitz set BG of isocrystal. So again, if G is GLN, this is just BG, just stands for isomorphism classes of rank n isocrystals, and basic just means isoclinic. And then, okay, you have a corresponding stratum, which I want to call it B prime. B prime, and this has a very explicit description. So it's just given by a classifying stack of a certain topological group. So GB prime is a certain algebraic group, so it's an automorphism group of the isocrystal B prime. So it's an inner form of G. And you take its QP points, you get a locally profiled group, and you realize it as an arc stack by this underlying form. And here, everything is defined as a priori has functor on perfectoid spaces of characteristic P, but I will base change everything to K. So my S will always be perfectoid space over K. So K is really just the notation for the arc stack of K. Okay, so again, if in this example that I have, if P is 1, then G is just GLN. JB prime is just GLN, and if B prime is my B, then JB prime is the division algebra of invariant 1 over. And maybe as a side remark, where is this coming from? So basically, I'm looking at this stratum corresponds to the stack of the substack where my G bundle is semi-stable of Hardon-Narasimhan filtration prescribed by B prime, and so where it's isomorphic to B prime. And so the implicit claim here is just that the automorphism group of EB prime is given by this GB prime QP underline. So ultimately, this is really coming from the fact that when you look at global sections of the structure shift on the Fark Fontaine curve, that's the same thing as this arc shift QP underline evaluated on S. Right, so that's the idea that this is a complete curve over SPA QP. So it has no non-constant global section. Right, so that was point 1, and point 2 is the result that the category of vector bundles, sorry, not vector bundles, analytic QL bar, lease sheaves on D1, so local systems for any prime L different from P, div1 Hauck-Schöpfner. This category is the same as the category of continuous QL bar representations of the veil group of QP. And this is just a direct consequence of a very explicit description of div1 Hauck-Schöpfner. It's just, this can be just described as the arc stack of CP, complete algebraic closure of QP, by the action of the veil group. So it just follows from this explicit description. Right. But of course, this is very nice because you see that, well, on the one hand, you can do like the series of smooth representations of GQP itself just by taking B prime to B1. Is like sort of embedded in shift theory on Bungie, just by Schrick extension from the trivial stratum. And on the other hand, what you see on the Galois side of local Langlands naturally appears when you use div1.
Sorry, I'm confused about something. What does CP, why CP? Because I thought these are defined on characteristic P point spaces.
Yeah, so CP flat. Yeah. But that's basically the same thing.
Wait, sorry, I mean, is K CP flat, or? I'm still slightly confused here.
That's just the arc stack of CP.
Okay. Sorry, I mean, is div1 is like untilts modulo Frobenius? Does that?
No, that's correct, yes. Well, I mean, you can also rewrite as div1 as the arc stack of QP Brever, not Frobenius. So you get QP Brever because I base change everything from to perf K, right? So there is implicitly a base change to FP bar, which lets you pass from QP to QP Brever. And then basically I'm just, just using poetal descent to rewrite this as a quotient of arc stack of CP by the action of inertia. And this combined to an action of the veil. Yeah, so that's maybe the more standard description, and you get this one from it. Okay, right, so how do you connect? So now, this geometry gives you a way to connect the two sides. By standard construction. So I will pick V a representation of G hat, the dual group of G, which of course, if G is GLN, is again just GLN itself. And so then you have certain functors from analytic sheaves on Bungie. So they are not quite under functors because you see this div1 Hauck-Schöpfner appearing on the right, but this is really nice because it precisely gives you a way to somehow make the two sides, these two kind of geometry speak to each other. And so how do you get such functors? Well, very roughly speaking, the idea is that you can construct a stack which lives over both. Which is called the Hecke stack. And this itself mapped to something called the local Hecke stack. So what are these? So this is just parametrizing a divisor of degree 1. I won't give like a complete and precise definition, but basically you parameterize the degree 1 divisor plus a modification of G bundles away from D, meaning that you give yourself two G bundles and an isomorphism between them away from D. So you see that you have obvious maps to two copies of Bungie by just remembering these two G bundles, or to div1 by remembering the divisor, degree 1 divisor that you pick. And this is the same, but just everything is just locally defined. Same, but only on the formal completion of the far content curve along D. So So you have a far content curve over some perfect fixed space S, you have a degree 1 divisor, but your G bundles, you only consider them as defined on this formal completion. So that's a version of the, some incarnation of the Alpha-Grassmannian in this p-adic context. And so now, non-trivial result is that whenever you have such a V, it gives rise to, so V gives rise to a certain complex of p-adic sheaves on this local Hecke stack. This is a non-trivial statement. This is the content of the geometric Satake equivalence. And then you can use it as a kernel to define a functor from the left term to the right term. So you pull back, you tensor with the pullback of the Satake kernel, and you push forward. And so that's what you can do on the when you start from Bungie. But you can also do something, so to say, on the other side. So you look at LS. LS stands for local systems. G hat also the moduli of. I want to say very informally the moduli of QL bar. These sheaves on deep 1 Hauck-Schulze, but really the correct way to define this is as a certain moduli stack of representations of the Veil group with coefficients in some arbitrary QL bar algebra. And here as well, you have certain functor, which I will denote TV spec for spectral, going from sheaves on the stack to itself. And
sorry, a stupid question. What is G hat?
Langlands to a group.
Oh, okay. Sorry.
Sorry. Yeah, I should have rewritten this stuff. But okay, if G is GLN, this is just GLN again.
Sorry, also, just to clarify, so this LS is should I think of that as moduli of representations of the group?
Yeah, that's correct. Yes. So, like setting up the definition correctly is not obvious because you have to deal with like representations of the topological group. But this has been done by various people, including Hauck-Schulze. Yeah, but sorry. Here I'm going to be extremely sketchy because I don't want to.
Sorry, but is it an algebraic stack?
It is an algebraic stack, yes, over QL or QL bar. And here, when I write D, it's some version of the category of quasi-coherent sheaves. So this is different from the D I was using before, the DQL bar, which means like analytic sheaves, which is also something you have to work a lot to define correctly in this context.
Probably another stupid question is the Hecke, like local Hecke stack, like a Alpha-Grassmannian quotient by some G.
Yeah, basically that's what it is. Yeah, it's maybe a version in families because it's moving over D1, so maybe what people sometimes call the Bailey-Sandring Alpha-Grassmannian. Yeah, but you also model by L plus G. So after pullback to a geometric point, it looks like LG, like loop group modulo L plus G on both sides. So like a perverse sheaf on this is exactly an L plus G equivalent perverse sheaf on the Alpha-Grassmannian. Right, and so here, sorry, what do I want to say? Right. So how do you define such functors? Here it's much simpler to do than here. You need some very non-trivial input, which is geometric Satake. And here, after some unraveling, it's more or less very easy from the definitions. So basically, the idea is that V. So it's a representation of G hat. So you can just compose. I just say it orally. You just compose V, the universal G hat local system on this stack LS. You compose it with V, and you get a vector bundle, really a Veil equivalent. some equivalence for the veil group, and this action is just given by tensor and by this object. So there is implicitly some equivalence for the veil group, which is hidden here. Because a priori, if you look at my two Hecke functors, the picture looks a bit asymmetric because TV was not quite an endofunctor of D bun G. But here it looks like it is one. But it's really something, you should really think to the target as being something like LS times div1. Again, except that this does not literally make sense because div1 is an object in perfect Lie geometry and LS is just an algebraic stack over QL. So we need more technology to make sense of this, but the fact that div1 is basically just a geometric point modulo the veil group, it allows you to rewrite things just in this by adding some equivalence for the veil group. So you should really imagine that this is a bit analogous to what happens upstairs. And so Farg and Scholz's main conjecture, again in a very precise form, is that you should have some equivalence between sheaves on Bun-G, analytic sheaves. So I put like really big quotation marks. And the category of sheaves on this stack of G-check local systems. Sorry, here I should have said G-check value. In such a way which is equivalent for this action, well, again, suitably understood, of category of algebraic representation of the dual group on both sides via Hecke functors. So this is okay, and so a nice consequence of such an expectation is that if you know fix, so fix now rho. Let's say irreducible, and I don't think this is really necessary. Let me again, for simplicity, just go back to the case where G is GLN, an irreducible rank N veil representation. So it defines a point of the stack, so it corresponds to. So I can look at the skyscraper. Maybe I did not do delta rho, which I see as a coherent sheaf on this stack of parameters. Right, so rho corresponds to QL bar point of my stack, LS, G hat. And so I just look at the skyscraper sheaf at this point. So this has to, what I mean by this is really, like this has a non-trivial, even though it's irreducible, let's say the automorphism group in this case is just GM. So I really take the skyscraper corresponding to the regular representation of GM. And maybe I'll keep this. And so now you can just look at what Hecke functors do to this object. And you see that it will be, so if you apply for any V in a G-check, TB spec applied to this object, or you tensor a vector bundle with a skyscraper, so basically you just get the skyscraper again, tensored with a fiber of your vector bundle at this point. So you just get something like this skyscraper tensored with what I denote by V rho, so the composition of rho, which is G-check valued by my representation G-check. So if you believe in such a conjecture, then you are led to expect that to any such rho you can attach by the conjecture rho should give rise to some object f rho which is a complex of analytic shifts on Bungee Farchurse, with the property that so it's an eigenvector. So for any algebraic representation of G hat, TV applied to F rho will be isomorphic to F rho again, box product V rho. So V rho I see as a vector bundle on div 1, and so I just take the pullback along the two projections. So that's a very particular consequence of this general conjecture. And of course, this is all inspired by the geometric Langlands program, and maybe first by the geometric Langlands program over function fields, where this existence of Hecke eigenshifts corresponds via the shifts functions dictionary to the fact that global Galois representations for function fields should give rise to like automorphic forms which are eigenvectors for the Hecke action. But in this setting, there is no such dictionary, so it's also a priori totally unclear what this Hecke eigenshift property concretely boils down to. And we will see that this is just another instance of our original question. So let us unravel this by, so again for G being GLN, and let me just take V mu, the algebraic representation attached to my co-character mu. So that's just, so I recall that mu is 1, 0, 0, 0. So in this case, that's just a standard representation of GLN. And, well, something nice happened in this, what is called the minuscule case, is that SV, my Satake kernel, which of course is in general rather complicated, is up to some shift and twist. It's basically just a constant shift, QL bar, on a certain substack, which I will denote by Hecke G Fs mu of the whole Hecke stack. And what is this? Well, it's just modifications bounded by mu. So one way to say it is that, well, what it parameterizes is d, let me write it down, d integral 1 Cauchy divisor on Fark Fontaine S, E a G bundle, so rank n vector bundle on Fark Fontaine S, and S, which is a section over D of the following fibration in flag varieties. So you have E times G. So my mu determines a parabolic P mu, and that's just this flag G mu is just G mod P mu. So in this case, it would just be projective space of dimension n-1. But yeah, I try to use notation which keep a meaning in general. So this lives over Fark Fontaine S, and I want to pick a section. So basically, I give myself a rank n vector bundle, a divisor, and just on the fiber of this rank n vector bundle at this divisor, I want to choose a filtration of type mu. That's what I'm saying. Right. So now let's pull back. So let me call this star, and let's pull back star along the embedding of the stratum corresponding to my B inside all of Bungee. And so let's look at what we get on both sides. So I realize I forgot to say something important. So as I stated, this conjecture of Arthur-César has a priori maybe nothing to do with local Langlands. But of course I should have said that another expectation of them is that, moreover, so maybe that's just a continuation of what I was saying before. Expect that for any basic isocrystal, if I pull back, so this Hecke eigenshift restricted to the corresponding semi-stable stratum, well, so this stratum is just a classifying stack, so it just corresponds to a smooth representation. And we expect that it is as given by pi b of rho, where this is what you get by applying smooth local Langlands and Hecke Langlands. Right, so local Langlands allows you to pass from rho to a representation of, say, GQP. G is as I split, and then you can transfer between various inner forms of G using Hecke Langlands. So that's some of the compatibility between this geometric picture and like usual local Langlands, which for GLN is a non-result. And so of course I need this to identify what I get in this specific example. So let's come back to this pullback. So on the right hand side, if I assume this, then we just get V rho downside with, which is just V being the standard representation. I just get rho, and the other thing is just pi b of rho. And again, because of my choice of V, this is just really smooth representation of the division algebra, units in the division algebra of invariant 1. So that's what you get just directly from everything I said on the right-hand side. On the left-hand side, it's a priori more complicated because it involves this Hecke operator. But so now I can use what I just explained. And so you see that, okay, so you have one GFS as part of your Hecke diagram. You have this, and now you are only interested in what happens after pull back to the stratum corresponding to B. So you are pushing something here and then pulling back. There's a strict push forward. So by proper base change, you see that you only need to look. So let's see if I want to give it a name. Yeah. Maybe I don't want to introduce too much notation. So you have first to, that's the same basically as just pulling back further to this and pushing forward. And using the description, the explicit description of the kernel, some unraveling gives you that you are the left-hand side is computed as the pi 1 of rho, which is just usual local Langlands of rho for GLN itself, isotypic component in the push forward of F, let's say F lower shake QL bar, where F is F is a morphism from maybe this one I want to denote with a tilde. For later, what I really want to be called Hecke GFS mu. I think there are always too many notations in this subject. So do I have? Sorry. All right. So let me write and then explain. So you can just push forward this to D1. So what is this? Well, it's basically you have Hecke G Fs mu tilde as defined before. This leaves over two copies of Pan G by definition. And now you just pull back to the point which corresponds to the one corresponds to just the trivial vector bundle, and the other one corresponds to the vector bundle of slope 1 over n. And you form the pullback, and that's what I will call Hecke G Fs mu b infinity tilde, and then this is just the quotient by Frobenius. So when I write without tilde, it means quotient by Frobenius. Any diamond comes equipped with a Frobenius. This Frobenius is just there because a priori, no, maybe the way I wrote it is fine. I'm sorry, forget about this tilde. That's better. No tilde at all, also upstairs. Sorry, the way I explain it, maybe it make it look like complicated, but it's really just the reason this arises is really just like by this kind of reasoning I was starting to make over there. You want to compute the fiber on a particular stratum using proper base change. You have to do a base change, and what you input is like maybe a representation supported on the trivial stratum, and then this means that if you unravel, this is like computing some cohomology for the GLNQP action of this tensor with the further pullback, while you also trivialize this other one. Okay, so that's what the left-hand side gives you. But now, you see that from the definition, by comparing with what I have still on my board in the middle, on top, from definition, we see that Hecke G mu b infinity is just the same thing as the diamond of Fg mu, and now maybe modulo Frobenius. Because no, before the untilt was not really considered up to Frobenius, and now since everything is defined as degree 1 divisors on the curve, it's really there is a Frobenius. I'm modeled by Frobenius implicit. Right? There is lots of notation, but that's really just from the definition. You are looking at I have two G bundles with a modification of type mu between them, mu being 1, 0, 0, 0. And moreover, by doing this pullback here, I have fixed one of them to be with a trivialization with E1 and the other one with a trivialization with EB. So I'm really just looking at such morphisms U with the properties that the cokernel is of length 1. And so, what's the conclusion out of this? Is that a Hecke eigenshift property plus the compatibility with local Langlands and local Hecke Langlands in the conjecture of Hauck-Schulze, it really implies this equality, the isomorphism you have specialized to this stratum. It implies that local Langlands and also at the same time local Hecke Langlands are realized in something you could call the L-adic completed cohomology, because it's really cohomology at infinite level, but with L-adic coefficients of the Rappaport zinc space MGB nu. Because literally what this isomorphism is telling you is that when you take this pi1 rho isotypic component in this cohomology, this push forward is just computing maybe compactly supported cohomology, L-adic cohomology at infinite level. you get the Jacques Langlands correspondent tensor with the local Langlands correspondent of your computation. So that's the meaning of the Hecke-Eigenschicht property in this local p-adic context. It's kind of explaining you, well, explaining, I don't know, it gives you a different perspective on this kind of statements and the most general version, which is called the Kottwitz conjecture. It took me much more time to answer, of course. Are there any questions about this?
So the quotient by Frobenius disappears when you compute cohomology because diff 1 is also something.
I mean, it's really because it's really what you want if you want to see. Like div 1 also has a quotient by Frobenius in its definition. So by pushing forward to div 1, I get something like a complex of representations of the vein group. So that's really the analytic cohomology, not only with this group action, but also with this vein group action. Also questions about this?
Maybe just a quick question. So I guess for this, it's very important that this SV is up to a sheaf / just a constant sheaf. And doing this more generally would become more complicated. It would be the cohomology with some coefficients of the solution.
Yeah, in general, you get a much more complicated formula. Also, the relation with local Langlands and local Jacques Langlands is much more involved. Like, where is it? Yeah, this statement here, like it's really like that for GLN, but in general, you have endoscopy phenomena, and so the actual description of the fibers is much more involved. But there is a precise conjecture. Maybe classically formulated for Rappaport spaces, but I think it has been extended by work of Hansen, Kaleta, Weinstein. So this Kottwitz conjecture, which describes the cohomology of local Shimura varieties, and maybe also even in the non-minuscule case, gives a precise formula for the cohomology. So kind of very general version of the claim I was making. This is, by the way, known in this particular case by the work of Harris Taylor. Long before fractures. Okay, that was, I thought that would take me half an hour, that was optimistic. In the remaining, okay, then I won't say as much as I expected, but let me try to explain now what happens with p-adic coefficients, since of course that's supposed to be our topic today. So what about p-adic coefficients? Alright, because of all this, maybe if you want to understand better what happens in completed cohomology, it seems like a good idea to try to maybe implement, like develop a similar framework as the one of Arthur-César. So for various reasons, it's not clear a priori how to do that with p-adic coefficients, but we saw in previous weeks how to upgrade like perfectoid geometry to this Gelfand geometry, where sometimes the basic idea was just that in your moduli problems, you can always replace perfectoid rings by over-convergent seconding of such, what we call nil perfectoid rings. And actually, we saw already how to define a relative Fark-Fontaine curve over any nil perfectoid ring. So let's just do that. So let's just use this to, I will know to just go through what I explained in the fractal context briefly and say what you get. So define no bungee. No superscript anymore. So now instead of being an arc stack in characteristic P, it will be a Gelfand stack over QP. So it should be as. And so you send a nil perfectoid. Of course, there is no reason a priori to restrict to nil perfectoid rings over QP. It means concretely that I will only explain how to do how to try to do some version of p-adic Langlands with QP coefficients, but there is of course the expectation that you can also do something integrally or mod P, and for that you have to use and like this more general mixed characteristic setting that Maximilian explained to us. But let's stick to QP coefficients for today. But no, okay, the definition is obvious. You just take G bar naught on Farc-Fontaine curve over A, which is now this Farc-Fontaine curve, which I recall is like the Farc-Fontaine curve for the dagger reduction or uniform completion. And you do some over-convergence thickening along the untilt defined by this uniform completion. So that's something you can check is a Gelfand stack. And, well, we already have defined in previous weeks something called div1. And so div1 will stay the same as last week. So I recall it's just a perfect analytic prismatization of QP modulo Frobenius. And before I had this point, these main features 1 and 2, so what do they become now? So for Bungie, this locally analytic Bungie, you still have Hardon-Araziman certification indexed by the same set. And again, the semi-stable locus inside is defines some open substack, which again has the same kind of decomposition in connected component. And each of these connected components is a classifying stack, but now it's a classifying stack of GB, so P is B prime, GB prime QP locally analytic. And now the meaning of star has changed, so now this is just notation, short notation for G spec QP, because now all my functors are defined on QP object. So GB QP is a p-adic Lie, and I take its incarnation as a Gelfand stack using locally analytic functions. And the proof is basically, like the way you see that is basically the same as in the context of Farc-Schulze. So here the key claim is, if I write it in terms of Banach columnar spaces, I think that's the notation we used. It's just again coming from like the sheaf of global sections on this, of the structure sheaf on these nil perfectoid rings, which is just what BCO stands for, was computed to be QPLA. That's a simple computation just using the fact that this is a simple push-out. Okay, so instead of seeing, but no, another difference maybe with Farc-Schulze is that in Farc-Schulze we were taking analytic sheaves on this stack. Now we will just take quasi-coherent sheaves in the sense of analytic geometry on this stack. And again, because it's an open substack, any of this strata, by Hecke extension gives rise to a fully faithful embedding of solid locally analytic representations of G, let's say GQP when B prime is 1, inside the category of quasi-coherent sheaves on G. Yes?
So I should really think of this as more like the Durham stack or something. Because you're taking quasi-coherent sheaves instead of analytic sheaves. Is it something
in some sense, yes. Yeah, that's maybe one way to think about it. Like, actually, you could also take the Durham stack of this one, and maybe I will come to this at the end. Yeah, so that's right. Maybe an analog in other settings would be like, let's say in Durham geometric Langlands, instead of speaking about D modules on the usual Bungie, you can speak about quasi-coherent sheaves on its algebraic Durham stack. In some sense, yeah, the definition of Bungie is made in such a way that it's already incorporated in its definition. Okay, but so we see locally analytic representations of GQP in the category of quasi-coherent sheaves on this Bungie. That's one thing. And for the other one, well, completely parallel, so except that now we use quasi-coherent coefficients. So instead of looking at local systems, I will look at vector bounders. And vector bounders on div1 is just the same as the category of phi gamma modules over the rho bar. Curly R. That we have seen several times, but for sure last Friday, I even stated a much more general statement, which gives you a description of the vector bundle or perfect complexes on the twistor stack of any smooth rigid space, partially proper over QP, in terms of vector bundle on perfect complexes on the relative far fronted curve. So in this very particular case of spec QP, it just comes down to this claim. And that has been known to be the correct replacement for the notion of p-adic Galois representation in the context of p-adic.
So what's this R here?
R is for barring.
Oh, okay. That's an equivalence of Lue-Pan stacks.
This may be a clever
This is a fixed statement. Sorry, you're saying this is a fixed statement. Sorry, is it a fixed statement or is it like a statement to functor? Is it equivalence of functors or? Sorry, is it equivalence of stacks or?
but which stack, sorry?
I'm slightly confused because I thought the phi gamma modules are the same as Galois representations over a point, and they become different.
That's only true for étal phi gamma modules.
Oh, so even for QP it's not.
Even for QP it's wrong. Yeah, if you drop this étalness, but that's maybe something that the study of locally analytic p-adic Langlands made people realize, that when you do locally analytic, then it's better to drop this étal condition and really replace p-adic Galois representation by this category. Then maybe you're of course, then you can try to define a moduli stack of vector bundles, or more generally G hat torsors on div 1, and you expect some relation with the so-called Emerton G stack. I mean, the variant of which has been constructed, maybe mostly studied by Hellman over the Hobering. But this is a more difficult question. I don't have much to say about how this construction relates to whatever Gelfand stack you can try to define.
But also, sorry, so there's also vector bundles on the far 10 curve as well as vector bundles.
Yeah, so maybe here this equivalence goes in two steps. So by this decompletion result from Friday, this is the same as the category of vector bundles on far content QP diamond. That's I explained that you have this natural, for any, much more generally, if X is smooth, partially proper, you have this morphism to the twistor stack, and the claim was that pulled back along it induces an equivalence on vector bundles, even perfect complexes. So that's just a special case of this more general claim. Right. And then the second step is just identifying these two categories, whether that's a standard statement. I'm not saying it's obvious, but it's something that is already. Okay, and so that's nice. So let's just widely speculate and imagine that we try to formulate some categorical conjecture in this setup as well. Well, then we would, more or less for the same reason, we would be led to expect that there are Hecke eigenshifts associated to parameters, to L parameters, and the same kind of unraveling it would lead you to consider objects analogous to this one. And the question is what's the cohomology? So when I do such a computation, what exactly do I get?
There's no version of geometric Hauck.
Yeah, so that's why I will only look at the minuscule case.
Right, okay.
Yeah, exactly. Yeah, so that's of course one of the things we don't understand at all for the moment is how to get this, how to define the Hecke kernels in general. But yeah, in the minuscule case, you can just take them to be the structure sheaf, basically. So my G and mu will be always as in the beginning. And so you see that if I define, let's just mimic the definition of Hecke G mu. So define exactly as before, but using nil perfectoid rings instead. So you see that this definition, we will still have it. Yeah. This definition up there, it still makes sense, just replacing S by a nil perfectoid ring A. So let's just define Hecke G mu in the same way. So then maybe I want to introduce two notations. So define in addition. So this will be living over two copies of Bungie. And so I want to do the same base change as before, but I will do it in two steps. So you have Hecke G mu B, which is just a pullback. So it's defined to be the pullback of Hecke G mu. And you pull back to this trivial stratum and to the stratum associated to B. And then you can do a further pullback and then define Hecke G infinity B mu. So this one is really analogous to the one we had before. So Bungie 1 and Bungie B, as we just saw, are just classifying stacks. So I can just pull back to the point, which is just, yeah. Okay, but so, no, this one you can write a formula for it. So, and with a little bit of unraveling again, so you see that you are looking at, so let's say you have two G-torsors. One of them is isomorphic, but you did not fix the isomorphism to the trivial bundle. The other one is isomorphic to EP. So let's fix such a, for example, let's pick a trivialization of the second one. Let's pick an isomorphism with EP that just will define a GBQPLA torsor. And once we do that, we see that we are just parameterizing like modification of type mu of this one, and we want them to be, apparently there are several possibilities for such modification, we want them to be semi-stable of slope 0. So that's a certain condition. You won't get the whole flag variety, but a certain subtype. So what I claim is that Hecke, by this kind of reasoning, you can identify Hecke G mu B with what? So you have to monod by GBQPLA, because my description before was involving a choice of trivialization. And then you get, so not the whole flag variety, but a certain open subspace, which is called the admissible locus, so A stands for admissible. And then you take the twistor stack. Right? So again, the admissible is a condition that my modification is of EP is semi-stable of slope 0. And the div 1 is just because, well, we have fixed the trivialization of this E, and then we pick a section of a flag variety over D. But that's by definition, morphism from D to a rigid space X is what defines the p-adic twistor stack of X. So that's really just a consequence of the definition. And in this particular case, so in our situation, I repeat that flag G mu is just Pn minus 1, and this admissible locus inside is just the infill space. Sorry, maybe. Sorry, I think I said it wrong. I have to take it back. So if I do it in this direction with this choice of B, then in this case it's everything. Sorry. the situation is not, you have to decide whether you want to pick a trivialization of this one or of this one. And that gives you different descriptions somehow. So here, the fact that the admissible locus is everything is just a claim that if you look at a let's do just GL2. If you look at a modification of O1/2, which is of degree O minus 1, so it has, you see that the only possibility is that it is isomorphic because O1/2 is semi-stable. You see that the only possibility is that it is given by the trivial rank 2 vector bundle. So in this case, the admissible locus is everything. If you try to do it the other way around, you fix the trivial rank 2 vector bundle and you look at degree +1 modifications. Then two possibility happens, O1/2 or O plus O of 1. And this defines the stratification of P1 in this case, which is omega and it's P1QP. Yeah, that's all. Right. All right, so that's one formula for this pullback of Hecke GU. And now what happens when I pass to infinite level? So I further pull back to the point. That's my second pullback. So you see that Hecke G infinity in mu. So maybe I should say here. This morphism is an open immersion. But now this is a G QPLA times GB QPLA torso. Right, so after doing this further pullback, I get a GB QP times GQPLA torsor on this quotient. So this allows me first to get rid of this first quotient by GB QP. And this is therefore a GQPLA torsor over the p-adic twistor stack of like G mu A. Right. But now I can invoke the theorem I stated last Friday, this decompletion theorem for p-adic Lie group torsors on the twistor stack. One can check that after perfect realization, this torsor, how to say that? Maybe I don't want to say perfect realization, but let's say after pullback to the relative curve, so to Fark Fontaine of like G mu A diamond along this morphism alpha when X is a admissible flag variety. This torsor, this gives me a GQPLA torsor on this relative curve, and this one you check is coming from the GQP underlying torsor given by this infinite level rapproporting space, this time, on like G. So we discussed last Friday how if you have a torsor on diamonds, it gives rise to an induced torsor on Fark Fontaine curves, and then you can even upgrade this to a torsors for the local analytic vectors. But we also and then I also explained that GQPLA torsors on the relative curve or on the twistor stack, there is an equivalence between such. And this equivalence, it's how you pass from. So in one direction, you basically do this pullback, but conversely, how do you produce this torsor? So what I explained on Friday, this implies that Hecke G infinity mu B is in fact isomorphic to, you take the Fark Fontaine curve, relative curve, over this infinite level rapproporting space. So that's so that's almost a Berkowitz space. And now you take locally analytic vectors for the GQPLA action. Right, so that's just this general formula for decompletion by locally analytic vectors of torsors. I mean, here I'm really cheating a little bit. First of all, I would have maybe to also extend scalars, maybe pass everything is living over QP brevet. To make this really perfectoid, I have to maybe extend scalars to the cyclotomic extension or something like this. But also, this theorem of this formula is stated only assuming that this, when I take like this locally analytic decompletion of this Berkowitz space, it is what I call classically decompleted, meaning that there are no higher locally analytic vectors. But there is a way to formulate things which do not give such a simple formula, but still tell you that on cohomology you get the desired conclusion. So what's my conclusion is that because of this, you will see that when you do this Hecke operator computation, so you see that Hecke operator in this locally analytic context is computed as like basically some isotypic component for the GQP action. In the locally analytic computed cohomology of the Rapoport space MGP. Yeah.
Sorry. This isomorphism here doesn't look quite the same as the isomorphism in the middle board.
As the isomorphism what?
I mean, there's an isomorphism in the middle board where it says from definition, middle bottom.
This one you mean?
Yeah, I mean, they just don't look quite the same because of this GQPLA. I don't know if I'm supposed to.
Yeah, it looks. I agree. Like it looks a bit different. Like this, in the context of fractals, everything is defined as functor on perfectoid spaces in characteristic P. But here we work over QP, so implicitly maybe when you try to compare to, if you pass to the RAM stack side, then basically you get this kind of formula, but base change to the arc stack of QP. And this kind of base change is exactly taking, and then model Frobenius is exactly the definition of this relative far quantum curves.
Oh no, that I think I was
fine.
more confused about the appearance of GQPLA. Oh no, I think I understand. Okay, sorry.
Alright, so maybe I should have said, so here you have both an actions of GQP and an action of GBQP. I could also have taken GBQPLA local analytic vectors, in fact that keeps the same space.
Yeah, I guess, sorry, I have to interrupt because I see we only have like 5 minutes. So.
Yes,
Actually,
so,
we only have the room until 2:50, so it's
Yeah.
yeah, so let me just, right, so just finish in one minute. Right, so that's basically one conclusion I wanted to get to. And yeah, so if I had managed my time better, I wanted to also explain some statements about infinitesimal actions that Lue explained to us. For example, the computation of the geometric morphism for this. Well, it was in the global setting, but in this local setting of local Shimura varieties, how you can also extract it from this kind, from the geometry of this object. Thank you. Sorry.